Welcome back to the Foundry by Forge College. So, in our last explainer, we were deep in the weeds wiring things up with network configurations and Solana RPC nodes. But today, we're pivoting entirely. We're stepping straight into the forensic lab, throwing on our lab coats, and becoming Web3 detectives. Our mission today is all about observing and debugging Ether transactions. This is actually a really crucial part of our Understanding Ether Transactions module, which fits right into our broader look at comprehensive Ether handling and withdrawals for the Applied Solidity development track. Here is the engineering blueprint for today's investigation. We are going to cover the debugging toolkit, extracting evidence, inspecting the trace, building the timeline, and finally, the debug report. Section 1, the debugging toolkit. Equipping for analysis. Right, so before we can solve any on-chain mysteries, we've got to understand the environment we're working in. We need to clearly recognize the difference between a plain transfer and a complex contract invocation. A plain transfer, that's super simple. It's literally like handing someone a $5 bill. There's minimal execution and just a straightforward balance change. But a complex contract invocation, man, that's a whole different beast. That's like handing someone a $5 bill, but they have to lock it in a safe, update a ledger, call their mom, and if she doesn't pick up, they have to hand the bill right back to you. It involves nested internal calls, storage updates, revert conditions, and it can fail in some deeply nested, incredibly mysterious ways. So, how do we spot those hidden failures? Well, our primary magnifying glass here is the execution trace. Think of this trace like an airplane's black box, or maybe a security camera playing back a heist frame by frame. It is a step-by-step record of the EVM transaction's execution. It literally records every single move the transaction makes, meaning absolutely nothing can hide from us. Section 2, extracting the evidence, pulling data safely. Now, how do we actually pull this vital evidence down from the blockchain? We do it in 4 specific steps, and we use a safe local fork so there is zero real money on the line. Step 1, we run a mainnet fork via hard hat. Step 2, we fetch the transaction receipt using ethers.js. That gives us our basic landmarks. Step 3, and this is really the magic move, we call the debug_trace transaction RPC method. Finally, step 4, we save all this combined data straight into a structured JSON file. Basically, we're just bagging and tagging the evidence for offline analysis. With that JSON file safely saved, we can finally open it up and ask the million-dollar questions. And yeah, sometimes in Web3, these are quite literally million-dollar questions. We want to know, where did all the gas go? Who took our gas money? And why exactly did this transaction fail? Section 3, inspecting the trace, reading fingerprints. Okay, time to put that JSON file under the microscope. To build our case, we're hunting for 4 specific landmarks in the trace data. First up, the call tree. We need to track the root call and all the internal calls, keeping a very close eye on where the ether actually moves. Second, the opcode sequence. We want to scrub through that and find the absolute last executed command. Third is gas accounting. We've got to identify the exact hotspots that just guzzled up all the gas. And fourth, storage rights. We're comparing the state before and after the transaction to see what, if anything, actually changed. Now, our prime suspect in these investigations is usually the dreaded revert opcode. This is the blockchain's very blunt way of saying access denied, but rudely keeping your gas money for the trouble. Spotting this specific opcode in your sequence is the definitive, undeniable sign that execution was forcefully halted. When you spot the revert, boom, you've found the exact moment the crime occurred. Section 4, building the timeline, chronological flow. But look, evidence means absolutely nothing without context, right? We have to reconstruct the crime scene. The crucial part here is mapping out the transaction's lifecycle chronologically, from start to finish, using timestamps as our unit of time. We start with the mempool timestamp, like when did it first enter the waiting room? Then the block inclusion timestamp, when was it officially picked up? Next, we track the execution start and finish boundaries based on our trace. And finally, we drop in the revert or finalize marker. By lining these timestamps up, we can figure out if an issue was caused by some massive propagation delay or if it was purely down to the execution logic itself. Section 5, the debug report, synthesizing findings. All right, this is where we synthesize all of our raw findings. We meticulously map the observed evidence directly to our root cause diagnosis. And notice how we're separating mere guesses from hard analytical facts here. For example, if we see a massive gas usage, say 1.8 million, and a revert at a specific program counter, well, we can confidently diagnose an out-of-gas error in an internal transfer from call. Or, if we notice a missing storage def for a balance, we diagnose unintended balance retention or transfer suppression. It is all about tying the symptom directly back to the trace evidence. But hey, a good Web3 detective doesn't just solve the crime, they prevent future ones. So our report has to include architecture-aware recommendations. Based on the evidence, we might recommend implementing pullover push refund patterns to stop malicious contracts from blocking transactions. We might suggest adding strict gas checks before entering heady internal loops. And we definitely want to ensure that calling frames handle exceptions properly, rather than just swallowing errors silently and failing somewhere down the line. As you dive deeper into the applied Solidity development track here at Forge College, I want you to remember this golden rule. Traces are hard evidence. Never just guess why a transaction failed. Always treat your trace frames as the undeniable, factual evidence you need to justify any architectural adjustments you make to your code. If you can't point to the exact trace line, well, you haven't really solved the mystery yet. So, we've successfully solved the mystery of the failed transaction using our trace data. But that leaves us with a pretty massive, provocative question. How do we design secure deposit and withdrawal flows that simply don't fail in the first place? Like, how do we build unbreakable smart contract fortresses? Well, that is exactly what we're going to tackle in our next explainer on security and architecture considerations for Ether handling. We'll take everything we just learned in the forensic lab and apply it directly to defensive coding strategies. To keep exploring this subject and to level up on other Web3 topics, I highly encourage you to visit forge.college. There is so much more to uncover, and I really can't wait to guide you through it. Thanks for hanging out, and we'll see you in the next one.